Hey everyone! Welcome back. Today, we're diving into one of the most critical and intimidating parts of tech interviews, the system design interview, specifically geared toward FAANG companies, Facebook, Amazon, Apple, Netflix, and Google. But instead of just theory, I'll walk you through real-world scenarios, the kind of problems you'd encounter in production-grade systems at these companies. Let's not waste time, let's get into real-world scenarios. Before diving into the questions, let's set context. So, you're preparing for a system design interview at a FAANG company. You've practiced coding questions, maybe even solved hundreds of LeetCode problems. But then comes the system design round and suddenly, it's a whole different ballgame. What are they really testing you on? What does a good system design answer even look like? At the heart of it, FAANG companies are not looking for a perfect design. They're looking for your ability to reason through complex problems and make smart trade-offs under ambiguity. Unlike coding interviews where there's a binary right or wrong answer, system design interviews are about thought process, communication, and real-world decision-making. Let's break it down. 1. Problem decomposition. One of the first things interviewers are assessing is, can you take an ambiguous problem and make sense of it? Let's say they ask, design Instagram. That's intentionally vague. They're watching to see, do you ask clarifying questions? Can you break it down into manageable components? Feed, stories, notifications, messaging. Can you identify what to prioritize based on constraints? This shows that you're capable of handling real-world complexity where requirements are rarely complete or static. 2. Communication and structure. You could have the best design in your head, but if you can't communicate it clearly, it won't matter. FAANG interviews value structured thinking. Top candidates. Talk through their assumptions. Use frameworks, for example, define functional and non-functional requirements, then propose a high-level architecture. Draw diagrams, even virtually, summarize each step before moving on. Think of it like pair designing with a team. Can your interviewer follow your thought process? 3. Trade-off analysis and decision-making. Every system design involves trade-offs. FAANG interviewers want to see, do you know the cost of using SQL versus NoSQL? Do you understand when to favor consistency over availability? Can you justify choosing a message queue versus direct communication between services? They're testing your ability to reason through options, not memorize a checklist. A good answer sounds like, we could cache this data in Redis to reduce DB load, but we'd need to handle cache invalidation. The trade-off is added complexity versus performance gains. 4. Scalability and performance. FAANG companies build for millions to billions of users. They want to know, do you understand how your system handles growth? Can you design for horizontal scalability? Have you thought about load balancing, sharding, replication? It's less about solving now and more about designing for future scale. For example, we'll shard our user database based on user ID to distribute load. To handle high QPS, we'll use a CDN to cache static content close to users. 5. Technical depth. You don't need to be an infrastructure engineer, but FAANG companies expect technical depth. Can you dive into data modeling when needed? Do you understand how message queues, databases, and caches work internally? Are you familiar with concepts like rate limiting, back pressure, eventual consistency? Bonus points if you can relate to systems you've built. At my last company, we used Kafka to decouple services and handle spikes in traffic. 6. Reliability, security, and monitoring. Real systems break. FAANG wants to know, how would you handle failures? What happens if a node goes down? How do you monitor and alert? Is your system secure from abuse or data leakage? Add these thoughts to show maturity. We'll add rate limiting to prevent DDoS attacks and set up Prometheus plus Grafana for monitoring. Scenario 1, imagine you're working at Bitly or Twitter. They want a system that converts long URLs into short, shareable links. Key requirements. Short URL, long URL redirection. High availability and low latency. Analytics, how many times a URL is hit. High-level steps. Accept URL and generate a unique hash, base 62 encoding of an ID or random string. Store in a key-value store, key = short URL, value = original URL. Add caching layer, for example, Redis, for frequent requests. Use rate limiting to prevent abuse. Add analytics using Kafka or event queue for async logging. Scalability concerns. Shard based on hash prefix or consistent hashing. Scenario 2, you're building the add to cart service for Amazon. Sounds simple? It's actually complex. Key Key requirements: session management, idempotency, no double adding on refresh, item availability and price updates, design considerations. Cart service should be stateless. Use session ID to store state in a distributed cache like Redis. For persistence, write to a document DB like DynamoDB or MongoDB. Cart should be stored with expiration, maybe 30 days. Use event-driven architecture to notify pricing availability microservices when items are added. For scale, partition data by user ID. Trade-offs: do you favor consistency or availability? What happens when price changes after an item is in the cart? Scenario 3. Imagine you're at Instagram, tasked with building the feed that shows photos and videos from people a user follows. Key requirements: feed must be fast, personalized, scale to millions of users. Two main approaches. Pull model: when user opens app, we fetch latest posts from their followees. Push model: when someone posts, push that post to the followers' timelines. FAANG companies often use a hybrid approach. Data modeling: store user-follow relationships in a graph DB or adjacency list. Use fan-out on write for push model, distribute posts to all followers' timelines in Redis or Cassandra. Use message queues for a scalable fan-out. Consider pagination, caching, and ranking algorithms. Challenges: cold start for new users, viral posts, real-time updates. Scenario 4, build a file storage and sync system like Dropbox. Key requirements: upload, download, delete, version control, sync across devices, permission and sharing, design plan. Break files into chunks, store in blob storage like S3, metadata stored in a relational DB. Use hashing for deduplication, for example, SHA-256. For syncing, use long polling or WebSocket for real-time updates. Versioning via mutable file chunk references. Security and sharing, use signed URLs for access control. ACLs for folder permissions. Scale tips: shard metadata DB by user ID. Use CDN for fast downloads. Scenario 5, you're designing a video streaming platform like YouTube. Key requirements: upload, transcode, stream videos. Handle millions of concurrent viewers. Adaptive bitrate streaming. Core design: user uploads, stored in raw format. Backend workers transcode into multiple formats, 480p, 720p, etc. Store in distributed blob store, like S3. Use CDN to serve content close to user. Use HLS- protocols for adaptive bitrate. Other concerns? Video metadata in SQL or NoSQL DB. Comments, likes, equal sign, separate microservices. Content moderation pipeline. Scalability: use async queues for transcoding. Separate cold and hot storage. Final tips. When you're solving any system design problem at a FAANG interview, follow this structured approach. 1. Clarify requirements, functional and non-functional. 2. Define APIs, if relevant. 3. Design data models, ER diagrams, storage choices. 4. High-level architecture, clients, services, DBs. 5. Deep dive into components, caching, queues, CDNs. 6. Discuss scale, sharding, replication, load balancing. 7. Handle trade-offs, cap theorem, cost, complexity. Communicate out loud as you go. It's about collaboration, not getting it perfect. Thanks for watching. If you found these real-world scenarios helpful for FAANG-style system design interviews, give it a like, subscribe, and comment your toughest system design question below. Want a deep dive on any one of these? Let me know, and I'll see you in the next video.